first thing we're looking at is the oscillation of a mass on a spring. Now we're going to do this without friction and not hanging vertically for right now. Although at the end of this section I will hopefully remember to tell you something special about if it is hanging vertically. Alright, so let's think about what the setup would look like. Here we'll have a wall, here we'll have a floor. We're going to set mu equal to 0 because there's no friction. We'll set up a spring, and attached to that spring we will have some mass. Alright, spring has constant of elasticity K, and the mass is mass M. Now let's imagine what happens if I take this shape and I pull it out some distance, which for the moment let's call it x0. So it would now be sitting somewhere around here, and the spring would be very much stretched out, and then I let go. At the moment I let go, what are the forces that act on the mass? Well, okay, gravitation, sure, normal force, yes, but they're going to balance each other out. Other than that, spring force. So, free body diagram, I would have a normal force, I would have an mg force, but those are pretty uninteresting. N minus mg equals 0, so N is equal to mg. That leaves the spring force, which looks like minus kx. Now, you might be saying, well, why are you keeping the minus? Well, it's there inherently. Since I pulled it in the positive x direction, if this is my origin, my x equals 0, and I pull it in the positive x direction, the force will be inherently in the negative x direction. If I'd instead push this thing in the negative x direction, and you'll have to, excuse me if I'm pointing in the wrong directions for some of these things. I think I'm pointing in the right direction. If we push it in the negative direction, then the x would be negative and the force should be in the positive direction. And the minus sign being an inherent part of the force's description, it handles that for us. Now that one's a bit more interesting because it says minus kx must be equal to ma. And this is really where our story begins. I'm going to rearrange this into a slightly different form. It says ma plus kx is equal to 0. So I'll bring everything to the same side. And then I'm going to divide the m out, sort of. So I get a plus k over mx is equal to 0. And the last thing, acceleration is just the second derivative of the position with respect to time. Now, this is interesting because we've seen things that look a little bit like this before. This is a second order differential equation. All the other ones we've done so far have been first order, so this represents something that is significantly harder. You won't really be taught how to solve these until you take a differential equations class, or specifically this type if you watch a video I'll be posting related to it. Additionally, homogeneous, because it's equal to 0, and has constant coefficients. That k over m, k is a constant, m is a constant, so there's nothing at all special going on there. It turns out this is the second easiest class of differential equation to solve. And if we look at it, you can kind of see why. X must be a function that, when the second derivative is taken, is basically negative itself. So x has to be something where you take the derivative and it gives back something that's similar enough to itself that when you take the second derivative, you get back basically the same function, but with the minus sign. That suggests a very limited set of functions. For instance, one of the things that would work would be an exponential. Another thing that would work would be some kind of cosine function, potentially with a phase, or a sine function. Also potentially with a phase. So that's actually where we're going to go with this. For now, I'm not going to talk about in detail how you solve the general case equation, although I will talk about that in a supplementary video. But we're going to assume one of these forms. And since we already know it oscillates back and forth, that means it looks like a sine or a cosine. And I'm going to choose the cosine. So x, I'm assuming, has some form a cosine of, I'm actually going to call it not k here, but omega times time plus a phase. Alright. With that assumption, dx dt, the derivative of a sine is a cosine, the derivative of cosine is a minus sine. So we get a minus, we get an a, we get a sine of omega t plus the phase. We also have to chain rule the inside, so we also pick up an omega from this. Now we take the second derivative. Sine becomes cosine, so we keep the minus sign, we don't get another one. We do end up pulling out another omega. And we get this. If I plug those into the original equation, we have minus a omega squared cosine of omega t plus phase plus k over m, a cosine of omega t plus phase. Ooh, don't like that plus. Let's clean that up. And that equals 0. Alright, because that equals 0, we can get rid of the a, and we can get rid of the whole cosine omega t thing. And that leaves us with, I just realized you can't see a little bit of that second derivative, let me pull it up. That leaves us with this, which says minus omega squared plus k over m equals 0, or omega must be the square root of k over m. Great, so we just figured out the angular frequency that it has when it oscillates. And the best part, it's related to k and the mass. It's related to the spring constant and the mass. Things that we can get a hold of. Now, what about a? What about phase? Well, those will depend on the details of the release. You're going to have to think about your initial conditions. What was your x initial? What was your v initial? If you know that you release from rest at t equals 0, then you're probably going to be a is your initial release, your x naught. All right, let's pull some of this out. So that means we have x is equal to a cosine square root of k over m times t plus the phase. All right. The example case I just talked about was x is equal to x naught at t equals 0, release at t equals 0. So come back up here to where I did my drawing, pulled it out to some place, and at t equals 0 I let go. So that means if I set t equals 0 in the above equation, I have x naught is equal to cosine of the phase. And if I look up at this step where I take the first derivative, that means the velocity, which should be equal to 0 because I release from rest, is equal to minus the amplitude square root of k over m times sine of the phase. All right. So what can I do that makes these work? Well, the second one implies phase must be equal to 0, so sine of phi is equal to 0. And that works fine with the top one. It implies that x naught is equal to a, for instance. So we've got an example right there. Now it's a simple one. We'll look at maybe a more complicated example during the lecture on Friday, or whatever lecture we have associated with this. Whatever our together time ends up being. Okay. So to summarize, and then I will wrap this video up. If there is no friction and you have a mass attached to a spring, then you will find the position of that mass as a function of time will look something like amplitude cosine of the square root of k over m times t plus a phase, with a and phased determined by the initial conditions. Okay. So that's general for a mass on a spring. As long as we are at this, I guess there is one last little thing I should mention. Notice that in the velocity equation, minus a omega sine of omega t plus phase, this part right here represents Vmax. And that means Vmax must have a size of the amplitude times the square root of k over m. And if we look at the second derivative, which is the acceleration, we have a minus a omega squared cosine of omega t plus the phase. And this part represents the maximum possible acceleration, which is a size of a times k over m. So we've actually got quite a lot by way of result out of this. All right. So that's going to be it for the first video where we talk about oscillation of a mass on a spring.